Hi everyone, welcome to our paper relating simple sentence representations in deep neural networks and the brain. I am Sharmistha from Indian Institute of Science, Bangalore. This is joint work with Tang from Carnegie University and Partha Talukdar from ISC and Tom Mitchell from CMU. In our work, we try to understand relationships between language representations in deep neural networks and the brain. We know that brain is the best language processing machine. Currently, deep neural network models are doing very well in understanding language as well. We give both these models the same input, a simple sentence of the form, "the dog ate the bone," and then study relationships between the representations of the two models. In the past, Leila, in her seminal work in EMNLP 2014, showed that there is parallelism between brain activations and the deep neural network context layer representations. We extend her work by comparing multiple deep neural network models with the brain. In addition, we do detailed context evaluations to understand what the context at a given word consists of. Thirdly, we produce brain data from these deep neural network representations. Let's understand the brain data a little more in detail. We capture the brain data using magnetoencephalography, which is a non-invasive method to record brain activity. In this method, a subject is put in a scanner consisting of 306 sensors arranged around the head of the person. These 306 sensors capture magnetic activity induced by blood flow due to naturally occurring brain activity. This kind of data has very high temporal resolution of 1 millisecond, which is ideal for studying dynamic language processes. In our study, we provide the input sentence word by word to the user on a screen. Each word is shown to the user for 200 milliseconds, followed by a 300 millisecond gap. Brain activity is captured over all 306 sensors for this 500 millisecond time duration. We post-process the data by averaging 100 millisecond data in non-overlapping windows to produce a 306 by 5 size data matrix for each word. In our experiment, we record MEG data when human subjects are reading simple sentences of the form, "the dog ate the bone," and "the bone was eaten by the dog." Simple active and passive sentences. We have three such data sets. Pass Act 1 and Pass Act 2 consist of 32 sentences, both in passive and active voice, while a third data set, Act 3, consists of 120 sentences with only active voice. In these data sets, each sentence is collected for 10 repetitions. An average of these 10 repetitions is then used to represent the sentence. Repetitions help in improving signal-to-noise ratio in MEG data collection. Since the number of sentences in these MEG datasets is very small, we collect a separate simple sentence corpus consisting of active and passive voice sentences from Wikipedia and NEL triples. We collect 250,000 such sentences to train our custom deep neural network models. Following are the models that we use for comparing with the brain data. One of the first model is random embedding, where each word is represented by a random embedding generated. A second simple model is glove additive model, where a word is represented by its glove embedding, averaged with the previous word's glove additive embedding. A third model is a 2-layer BiLSTM language model, which is trained on simple sentence corpus. A fourth model is a multitask language model, which also predicts the pause tag for a given word. This again is trained on simple sentence corpus. We also compare the brain activity with state-of-the-art models ELMo and BERT. Let's look at our experiment setup for this study. The simple sentence is shown to subject and its brain activity is captured. The same sentence is shown to a deep learning model to capture the context representation. This context representation is then transformed using a linear ridge regression model into the brain activity. At the time of training, we use the true brain activity to train this linear ridge regression model, while at the time of testing, we calculate accuracy of predicting this true brain activity. With this kind of a setup, we try to understand the relationship between the brain and the deep neural network representations. In a first experiment, we evaluate each of the model layers' ability to predict brain activity accurately. Here we average the accuracy of each layer for all the stimulus in predicting brain activity. In a second experiment, we try to understand what the model's context at a given word consists of. In specific, we try to understand what the model context has retained from the past sentence by using brain as a reference. In a third experiment, we convert the deep neural network representations to brain data and use it for brain task augmentation. Let's look at these experiments in detail now. In the first experiment, we give inputs of the form "the dog ate the biscuit" and "the girl kicked the ball" to both the user and the deep learning model. The brain activity here is denoted by Y1 and Y2. Each of this brain activity is then the deep learning model representations are then transformed using ridge regression model into Y1 hat and Y2 hat. If the predicted brain activity Y1 hat is closer to the true brain activity Y1 as compared to Y2 in Euclidean distance, then an accuracy of 1 is given. Otherwise, an accuracy of 0 is assigned. This is a standard 2x2 test. What we find is that deep neural network layers are able to predict brain activity with good accuracy. In this graph, you see the best layers from each model and their accuracy in predicting brain activity. The random embedding model starts with a chance accuracy of 50%, which is further improved by better models. BERT mid layer, which is average accuracy from layers 14 to 17 in predicting brain activity, is the most effective in predicting brain activations. We also perform this analysis separately for each brain region, and we find that amongst all the brain regions, the left temporal brain region is predicted with the highest accuracy from BERT mid layer. This is an interesting result since left temporal region of our brain is known to be encode syntactic and semantic information at the time of language processing. In a second experiment, we try to understand in detail what the context at a given word consists of. For this test, we give the same sentence as an input to both the subject and the deep learning model and try to predict whether a standard 2x2 test can distinguish between this same word or same substring except one word in the past difference. So Y1 hat, which is for the dog, can it be distinguished from the girl kind of input? This is a harder test, and if there's a high accuracy at a given point, then we understand that the deep learning model is keeping similar context as brain. From this test, what we find is that for noun input, most of the deep neural network layers retain the information in the context, with the ELMo mid layers giving highest accuracy of 0.92. While for verb, input of the form "the dog ate the" versus "the dog saw the" are processed. And again, we find that most deep neural network layers retain verb information well, with again ELMo mid giving the best accuracy. However, for an input of the type adjective, where input "the happy child" is tested against "the child," middle deep neural network layers retain this adjective information better than the other layers, with multitask LSTM layer giving the best accuracy of 0.89. When first determiner is varied between two sentences, for example, "the dog" versus "a dog," then we see that shallow deep neural network layers retain the first determiner information better. For example, BERT layer 3 has an accuracy of 0.82 of predicting these two sentences as separate, as compared to BERT layer 18, which drops down to 0.78. In a third experiment, we note that there are various challenges in collecting brain activity. There is high cost of collecting MEG recordings of almost $60 per sentence. And subjects get typically fatigued inside these scanners quickly, and therefore cannot record data for more than 2 to 3 hours, which gives an upper limit of the number of sentences that can be collected in studies of these kinds. To overcome these challenges, we try to augment true brain data from BERT mid representations. How do we do that? We conduct an experiment where in Pass Act 1, we augment the 32 original sentences with an additional 160 sentences which do not overlap with original 32 sentences. These 160 sentences have the same vocabulary as the original sentences and are processed using deep neural network models. The deep neural network model representations are then transformed using a linear ridge regression model into brain activity. We test the quality of such transformation by doing a noun decoding and verb decoding task in the brain activity region. What we find is that there is at least an increment of 2% in accuracy by doing this kind of brain data augmentation. In conclusion, we studied the effect of prior context on deep neural network sequence representation and its relationship with the brain. This is one of the first studies to do that. We find that BERT representations are most predictive of brain activity, and BERT representations are useful in synthesizing effective brain data for downstream data augmentation tasks. Please find our code and paper online, and feel free to contact me if you have any more questions. Thank you.